Hi, everyone. I'm Gail Weiss. I'm a student at the Technion. And today I'm going to present to you a paper called Thinking Like Transformers that I wrote with my advisors, Yoav Goldberg and Eran Yahav, in which we attempt to understand transformers, or more specifically, transformer encoders. So, and of course, I can't actually. Why can't I change slide? Okay, now I can. So you may be familiar with transformers that came out in 2017 with the paper "Attention is All You Need," a new type of neural network to process sequences, which is actually made up of two parts: an encoder and a decoder. The encoder just takes a given sequence and encodes it into some set of vectors. Some very popular encoder that you may be familiar with is BERT, which all of these things are about processing an input sequence, and a decoder is more about generating a new sequence given an input sequence. So an encoder sort of processes an input sequence, and then the decoder gives some kind of response, we could say. So some decoders that you may be familiar with are the whole GPT family of transformers, the generative pre-training. So there's all kinds of bots online where they try and generate sequences according to various famous personalities. And in this work, we focus on the encoder. So what do we know about the transformer encoder? Well, people are doing all kinds of work. One paper is the R transformers universal approximators of sequence-to-sequence functions, which the answer to was yes. And in this work, Yoon and colleagues showed that for any continuous function from a fixed length input sequence of vectors to another fixed length output sequence of vectors of the same length, you could approximate that function in a transformer. This doesn't mean that they are necessarily all powerful, because we are dealing with fixed length sequences each time, but it is interesting about their ability to deal with fixed length sequences. Meanwhile, in the opposite direction, Michael Hahn gave the paper Theoretical Limitations of Self-Attention in Neural Sequence Models, where he proved that when we remove this fixed length sequence assumption, and specifically when we add a hard attention assumption, which isn't important at this moment, then we can't even recognize things like parity, which is a very, very simple language. We could think it's recognizable, I think, by a 2 or 3 state finite state machine. And yet a transformer can't handle it with hard attention and unbounded length. And with soft attention, the signal with which it is able to classify it strongly decreases with the length of the input sequence. And a couple of weeks ago, we had Satwick in here, and he with colleagues showed in the paper on the ability and limitations of transformers to recognize formal languages, all kinds of different languages which transformers do or don't struggle with, and how this affects their ability to generalize to different length, and generally explored in an empirical way their ability to deal with all kinds of formal languages, which was also very interesting. And then when we do get back to the encoder side, then we also have all kinds of results about Turing completeness. We use, sorry, not the encoder, the decoder side. And here we sort of use this ability to do multiple computations and do an output sequence of rather long length to have these sort of Turing complete calculations. So all of these give us all kinds of ideas about how strong a transformer is. But it doesn't really give us an intuition of how it's computing all of these things. Like, okay, so it can approximate a sequence-to-sequence function, but once we have a specific task that we want to do, how is it actually going to deal with that task? And if we look at recurrent neural networks, we do actually have some idea about their computational model. So what's a recurrent neural network? It's a neural network that takes as input 2 vectors, doesn't matter what these vectors are right now, and creates one new vector. And the interpretation of these networks is that one of the input vectors is an input token, and another one of the input vectors is the previous state of the neural network, and the new vector that they create is the next state of the neural network. And this is very similar to a finite state machine or just an automaton in general. There is an initial state, which RNNs also have, and the model is really just a definition of the transitions between these states, with the final classification being according to what the final state that we reach is. Is it a rejecting state or an accepting state in the case of binary automata? So we have this for RNNs, and through this, we're actually getting all kinds of ideas on what to do with RNNs. So we get extraction. How do we convert an RNN to a weighted finite automata or deterministic finite automata, or one of both, or a weighted deterministic finite automata, things like that. We analyze their expressive power using our understanding of deterministic finite automata. Second order RNNs are weighted finite automata. LSTMs are kind of like counter machines, which is an automata with a counter. Gated recurrent neural networks are kind of like finite state machines. We have all of these results. And we also get this intuition, what's stronger than a finite state machine? A finite state machine with a stack, a push-down automaton. Why not have that for stack RNNs as well? And so we have all this intuition, which we don't have for transformers, and it would be really nice to have it for transformers. So the point of this work was to come with a model that would serve the same purpose for the transformer encoder. The next slide is a list of references about what's in this slide. I'm not going to get into it. It's just there if you're interested. So all kinds of references. And now we want to have the same kind of model for transformers. So what would be the parallel for transformer encoders? Does anyone have any idea? Does anyone know how a transformer encoder works, maybe? It's okay if you don't, because I'm going to go into it.
Is it multi-layered, like deep, or just a single layer?
It is multi-layered, so are the recurrent neural networks. Unfortunately, that doesn't help us get to a model, I guess. But it's actually going to be relevant for the model in a moment. So let's take a closer look at the transformer encoder. What we've got is a model that receives, unlike the RNN, which takes its token one at a time, transformer encoders take their entire input in at once. It processes all the input tokens in parallel, and it applies this processing, just like you were suggesting, a finite number of times. It's a deep network, so it processes and then it takes the output and processes again, and so on. But it is a fixed number of times. That's just something that we'll have to note further down the line. So for a slightly more concrete example, we might begin with an input sequence, I like dogs, and we'll split it into two sets of embeddings. One is an embedding of the tokens, I like and dogs, and another is an embedding of the position. If you'll notice, because we're dealing with all of the inputs in parallel, unlike the RNN, and as we'll notice from the architecture, the transformer doesn't really know the positions of these tokens in the input, so we have to just tell it. So we get the positions, then we just sum them to get the initial encoding of our input sequence, and then we pass it through the first layer, get some kind of output, pass that through a second layer, and so on until we get our final output. So unlike a recurrent neural network, we don't have states, but we do have something else. If anyone has an idea what we have, what this feels like to them, we're sort of applying a set of operations, one after another, to our original input. So there's a sense of sort of, we're processing again and again. There's this information being propagated. It's the same sequence, but we're adding more information to it. We could hope, right? Maybe not adding, but making the information more accessible. So sort of if we put it side by side, we can kind of think of it like a very short program, which basically has the same number of operations as the transformer has layers. We make the tokens from our input, we make the indices from our input, we sum them, and then we begin processing them one after another. So it's kind of like variables, these outputs of these layers. So we say maybe we could abstract the transformer encoder as a programming language. And we really do present this programming language, the restricted access sequence processing language. Restricted access because we're going to try to mimic the same control flow, the same, not control flow, information flow constraints that the transformer has. So we're not going to do anything we like to these sequences. We're going to do what a transformer can do to these sequences, which isn't anything. So a transformer encoder is basically a sequence-to-sequence function, which we'll just call a sequence operator, or an SOP for short. Its layers apply operations to this sequence, creating more nicely processed information. And RASP is a programming language that isn't directly the SOPs, but it's the programming language that describes the creation of these SOPs, the operations that we can do between them, the ways that they are created. So RASP is just describing what the SOPs can be. And we'll get into that in a moment. Let's begin from the input sequences. So the input sequences are very simple. We're basically doing two things to our inputs. Before we do anything else, we get the tokens and we get the indices. So RASP begins by providing two variables, we could call them, but really they're constants in the language, tokens and indices, which are just functions that from any short input, from any input sequence, create a new sequence, once representing the characters in that sequence, and once representing the indices of the characters in that sequence. And there's a read evaluate print loop, and it really just shows you always examples of these functions, because otherwise all these variables are just of type, function to function, sequence to sequence, and you don't really have an idea of what you're dealing with. So it's always printing out little examples for you. Okay, so we have the tokens and indices. What are we going to do with them? In order to understand what we can actually do with these sequences, we have to look inside the transformer encoder layers themselves and understand what a transformer encoder layer can do. And so the first component that we're going to look at, because there is a lot in here, is the feed-forward sublayer. And this basically applies an element-wise feed-forward network to each of the vectors that comes in the input to the transformer encoder layer, or at least at that part in the transformer encoder layer. Now, there's already a result that feed-forward networks are universal approximators, provided there's enough layers and activations. And so we sort of take an artistic liberty here and assume we can do any element-wise operation, and we leave it to the RASP programmer to be responsible and ask themselves if indeed they are asking RASP to make some kind of logical or reasonable calculation when they're trying to make their abstraction of what a transformer can do. So for example, we've got addition. We can add 1 to our indices and get 1, 2, 3, 4, 5. Or we can do binary operations between two Boolean variables. And we can do a comparison to create Boolean variables. So we do tokens compared to E to see the presence of an E character in our sequence, or tokens compared to 0. We can do an OR between them, and then we get, that in hello, the second and fifth place have an E or an O. Is that making sense so far?
Quick question. Are these functions always operating element-wise?
So far.
Okay.
Excellent question. Are we all powerful, or at least transformer powerful at this point? The answer is no, because everything is element-wise. So excellent build-up. So we need to do something that is going to be more interesting, or we're never going to be as powerful as a transformer. So let's get back to the transformer encoder layer and see if there's anything in here that isn't element-wise. And of course, as the paper suggests, as the title of the paper suggests, there is one part of the architecture that isn't element-wise, and it's the multi-headed attention, and attention is all we need. So what is multi-headed attention? Let's begin from single-head attention just to understand how it works. We get our sequence of vectors, which is being propagated through the layers. And the first thing we do is apply two linear transformations to them, one creating a set of queries and one creating a set of keys. So this is just a quick linear transformation of our inputs. Now we're going to make a query is going to describe at each position the information that we want to gather into that position, what kind of information we're requesting. And the key is going to describe for each position the information that it will have to offer. And then when we do the scalar product between them, we'll get an idea of how good a match they are for each other, and specifically the key for the query, the token when the position when considered as input for the other position when considered as output. So we do the scalar product of the first query with each of the keys. We get 3 scores. We normalize these scores, that's useful for training. Then we softmax them and we get a set of weights, a distribution over the positions when considered as input for creating the new output at position 1. Finally, we apply a linear transformation to all of the inputs. This actually gets the information that we're going to want to gather and average into our output. We could consider this also as candidate outputs. We do a weighted average of these values, and we get our output at position 1. And then we repeat the same process with the second query to get our output at position 2. Yes? Someone said something? No, okay, sorry.
Sorry, I have a question. So we compute the keys which represent the contribution of this value before we compute the transformation.
So this is just for the narrative. We actually compute all of them at the same time because they're not dependent on each other.
Yeah, but still, the logic is that I want to measure the weight of a particular token based on its actual value transformed in a key. But later, when I go on to compute a value, I first transform it somehow.
Yes. So imagine that we have a sequence like, let's say, like I like dogs. And in the second position, we want to know not only that we're carrying the word like, but also that we're liking specifically a dog. So the information that we're going to request at that position, because we don't know that we're looking for a dog, we're going to ask for the object, or no, the subject, right? If I describe correctly, if I understand NLP correctly, we're going to search for the subject of the sentence, the thing being liked. And the third position in its key, it's going to say, I'm the thing being liked, I'm the subject. That's in the key. And then the query and the key, the query for the second position will match the key for the third position. But in the value, we're not interested in the fact that it's the thing being liked. We're interested in the fact that it's a dog. Does that make sense?
Yeah, I get that we have a separate transformation to make a key out of the dog, and because it's something that yeah. But then when we take the dog, we don't average the actual value of the dog, but we pass it through this intermediate transformation, which is called V here, right?
Yes.
So this kind of obscures the working of the model a bit. But yeah. So do we need this just to have more parameters there, or
I think you could imagine. So right now, maybe, and in this very rudimentary example, the only thing that you're imagining in the third position is that there's dog, but it actually also knows about itself that it's the subject, and it knows about itself that it's in the third position, there's a lot of information held in there. And when position 2 is going to gather the fact that it likes a dog into position 2, then now the position 2 won't only contain like, it will contain position 2, it will contain that it's a verb, it will contain that it likes a dog specifically, it may contain its relation to I. So it's gathering a lot of information into there. And the only thing that we really want to gather is the fact that it's a dog right now from position 3. So these vectors in the input, they're not just the token, there's a lot of information in there. And V, you could think of it as a selection of the part that's relevant to this gathering.
Okay, makes sense.
In a moment, we're also going to look at multi-headed self-attention, and there will be another motivation for V, if it helps give intuition. Okay, so hopefully with that, I will continue. Okay, so we do this for the second position, we get the output at the second position, we do this for the third position, and we've got our next output sequence, and all of that was a single self-attention head. Now for multi-headed self-attention, all we're going to do is take our long input vectors, the embeddings at each position, split them into H equal length vectors. They don't have to be equal length, but this architecture would have a lot of parameters if a lot of things weren't equal length, a lot of hyperparameters to decide on specifically. So we just decide they're equal length. We split them and we pass each of these split up blocks into the different heads. So here we have another motivation for V. We've kind of just chunked up our vector and maybe we want to clean up the mess that we've made and reorganize it in some kind of useful way. I don't know. So once we've applied our multiple heads, all we do is stick them back together in concatenation, and we get the output of our multi-headed self-attention. So this doesn't, there's no sort of dependence between these different heads. So it's not adding some kind of special new power. The only power it's adding is in the sense that a single layer can do multiple different operations because it has multiple different heads. So it is letting us sort of compress the operations into one position, into one layer. It's not making some kind of new operation that we didn't have before. And because of that, RASP, at least for the programmer, is not going to worry about multi-headed self-attention. That's an issue for the compiler, but not an issue for the RASP programmer. All the RASP programmer knows is that they have attention heads. So how are we going to present one head? Because that's all that we're going to worry about anyway. So a single head, in a sense, has two main actions. The first is creating these distributions, which will be used for gathering the sequences. And the second will be applying these weighted averages according to these distributions. So in the beginning, we're going to deal with the distributions, the scoring. Sorry. And we're going to deal with this as selecting. So it's even a simplifying assumption that we make. We're not going to worry about this sort of continuous, more interested in this token than this token, but generally interested in both things. We're only going to be interested in, are we interested in a token or not in our queries? So we're abstracting to just binary focus on or don't focus on decisions in the selection. And so let's give an example of how this looks in RASP. So here is an operation, and it's got multiple parts. The first part in the input to a select operation is the key. So that's the part that's treating the input, indeed, the different positions indeed as input, describing what they will have to contribute. And we're putting that on the top as a row of the keys. The second part is the query. So that's the part that's treating the positions as output, a description of what we want to put into them. And the third part is actually going to be the way that the queries and keys match. So that's not actually the way that it works in a transformer, but we're going to say these transformations, Q and K, we'll do some kind of meaningful transformation that allows us to do these different kinds of comparisons. Here we've put, for a simple example, just equality. And so we get this selection pattern. The first position wants input positions that describe themselves with 0, and so it chooses the last 2 positions. The second position, position 1, wants the positions that describe themselves with 1. Unfortunately, it doesn't have any of those, so it picks nothing. This technically can't happen in a transformer. We'll discuss how that's possible in the abstraction later, or how that is fair. The third position wants positions that describe themselves with 2, and so selects only the first position. If we had chosen a different type of comparison, let's say greater or equals, with the same descriptions, then the first position would have chosen all positions. 2 is greater or equal than all options. The second position would have chosen only the first position, and the third position would also have chosen only the first position.
There was a question in the chat.
Mm-hmm.
Is the last argument to select restricted to any Boolean function?
I don't know about any comparison. I think any. So I think we put equality, greater equals, less than equals, greater or smaller, or also possibly unequal. And we also allow composing selectors. So for instance, you can have a cell, the first cell that we have here, or cell 2, which would be just a logical and between the 2 maps. A logical or between the 2 maps. Again, a lot of the thing about RASP is that it's about giving us an idea of how the information flows. So it's, in the end, it's on the programmer to ask themselves, am I making an operation that's reasonable to expect a transformer to be able to make? So RASP doesn't answer that question. It answers the question of how would the information flow? What kind of comparisons and choices would I have to be making if I was a transformer solving this task? Does that help?
Yeah, it seems to help you.
Okay, great. So we'll continue. So another example, we could have, for example, prefs. So in this one, we want each position to focus either on itself or positions before it. So we've put effectively the indices as both the keys and the queries, and the comparison as less than or equals. And we get this lower triangular matrix where each position focuses on the position before itself. And we're asking, how would that look in a transformer, just for an example? Because you're sort of making this kind of a transformer in the self-attention, it's doing scalar products, and here we are with this less than or equal. This doesn't make any sense. So let's think how we could encode this nevertheless. So imagine that the keys of the different positions were just one hot embeddings of the actual position, and the queries could be multi-hot embeddings of the positions that we're interested in. This isn't a very efficient representation of this query, but it's an example of how we could, with the help of these scalar products, still get this relation that we're looking for. And has been abstracted away to something a little different in RASP, just for convenience, because that's the idea. Okay, so the next thing we've done, we're doing after we've got the selection pattern.
Wait, Gail, can I ask you a question?
Yeah, of course.
So here you're basically reducing this select less than or equals to a more primitive select where the relation is some kind of comparison, some kind of relation defined with the dot product. It's like max of x dot y, something like that.
Yes, it's any x dot y, right?
Okay.
Like if it's not, I didn't understand max, but yeah.
Okay. Well, how does the truth value come out of the dot product? Like if you were going to write it with the same.
So if we had just this, we'd be getting, for every query and key we'll multiply, If the index of the key is less than or equal to the index of the query, we'd get the scalar product of 1, and otherwise we'd get the scalar product of 0. And unfortunately, that would mean that under softmax, we'd have a sort of not a perfect focus on just the less than or equals positions, but also a slight focus on the remaining positions, because softmax doesn't just binary split the two.
Right.
But if we, I think with a great enough scale, so if we increase the size of these embeddings from not 1 but to 10 or so on, then softmax would begin to approximate this sort of hard selection of you were less than or equal and you were over, so your probability is close to 0.
Right. Makes sense.
Okay.
Cool.
No problem. Of course, how we would do that with a very long sequence would force us to be dependent on a large embedding size as well. But maybe this is reasonable because I don't think we deal with overly long input sequences to transformers anyway. And hopefully that's a better representation than the one I've shown here. So let's continue. After we've made our selection pattern, then we want to aggregate, as in average, the values that we've created. And so the aggregation is a straightforward operation. We're just going to apply an average to the selected positions. Sorry. So this is simple. We're just going to say there's an aggregate operation. It takes a selection pattern that we've just created. It takes the values, again, some kind of sequence, right? If we imagined that each position contains a lot of information, then let's say we take just the tokens or just the positions or whatever it is that we actually want to gather. And it just does the weighted average. So the first thing it does is, with the binary selection pattern created by cell, that's in orange on the left, we apply a filter to the values being aggregated. So we had 1, 2, 4. The first position only chose the 2 and 4. The second position chose nothing. The third position chose the first position. And we just average each one of them. So first position chose 2 and 4, and so on. And then we average each of them. And here we have decided on a default where, okay, in the first position, 2 and 4 became 3, but in the second position, we picked nothing and we put a 0. And that's, again, a sort of cheating in the abstraction, which we can later discuss what it would actually look like in a real transformer. And now, because sometimes we may want to aggregate over tokens, and because RASP is a symbolic language and we don't want to fall into, the numeric representation of A in an actual transformer, then we allow to skip the averaging when only one position is selected. And this allows us to transfer tokens back and forth. So for example, if you imagine that we have a reversing selection pattern, and we want to reverse our input sequence, then we can just apply an aggregation with this flipping pattern onto the tokens and get the reversed sequence without having to worry about the numeric representation of doing this. Hopefully so far so good. And so if we continue, we can actually really do reverse in RASP. The first thing we're going to do, if anyone has ideas, then they can suggest them, but if not, then I'll just go through the example. So what we're going to do is we want to focus each position on its opposite position. So we're going to create the reversed indices. We're going to take the length, subtract the current indices, and subtract an extra 1, to sort off by 1 issue. And we're going to use that for the key. We're going to use the indices for the queries, or maybe I've said that the wrong way around. No, I haven't. And then we're going to use equality for the actual comparison. And we're going to get a selector that aligns the tokens in reverse order. So first position chooses last position, second chooses penultimate, and so on. And then we're just going to apply, like we saw in the previous slide, we're going to aggregate our tokens with this reversing selector. and get the reversed input sequence. So we're going to get a sequence operator that on hello outputs OLLEH. Is there anything suspicious in this example?
I don't see it as a problem, but I think that the equality between the L's, it wouldn't be a perfect reverse matrix.
The equality between the what?
So there's two L's, and so if you're using equals as your comparison operator, I don't think it would cause any problems in this case, but
But I think it depends on indices, right? So the letter L does not matter.
Oh, I see. It's on indices, not the tokens. I see.
Yeah, in this particular case, we've hoped that Q and K, the transformations, have removed the tokens component and only focused on our indices in the way that we've asked them to. So we get this reversed pattern. So the actual suspicious thing in here is that I've used length, and I haven't actually said that RASP has a length sequence operator. And we know that transformers, as part of their input, don't receive the input length. We know they just receive the position of each token. So I'm going to have to prove to you later how we can still compute length and why it was okay that we did this here. Another thing that's interesting, just to point out, is that the select decisions are pairwise. So we haven't created some kind of arbitrarily powerful selection operator here that could focus each position on each other position according to some complicated calculation on the entire input sequence. And if we had, we could hide arbitrary power in there, right? Like if the select operation could just have the input sequence and do any kind of focusing, then we could effectively be Turing complete, because we could decide that the first position in the V outputs true and the second position outputs false, and our selector would do the whole calculation and just focus us on the first or second position. And also it wouldn't be a parallel to transformers, but it was important to make sure that the select decisions are pairwise. And that is actually the main transformer components, at least in RASP. So we've got the initial sequences, which have been abstracted to the indices and tokens. We've got the feed-forward sublayers, which have been abstracted to our various element-wise operations. And we've got the attention heads, which have been abstracted to the pairwise select and then the aggregate operations. But there are other things inside a transformer. So another thing that's valuable is the skip or residual connection. And this is a connection where we make some kind of calculation in some part of the transformer, but then to the output of that calculation, for example, the output of the feed-forward sublayer or the output of the attention head, we add back the value that was in the embeddings before we applied this transformation. And this also encourages this idea that information is retained through many layers. Much like a program, a variable that we created on line 3 is still there for us to use on line 10, even though we've done stuff with it since, so long as we haven't edited it, and we can't in RASP. It's once you make something, it's there, it's functional. So that's important. And another thing, another thing in the transformer layers is the layer norms, which are very useful for learning, and which frankly we're not entirely, so some people are doing interesting work on this, but RASP itself does not take layer norms into account, and we're not sure how it affects the transformers, whether positively or negatively. So that sort of remains open how that goes into it here. But we ignore it for now. So we've got RASP, it's got initial sequences, it's got element-wise applications of various operations to the sequences, and it's got the selectors and aggregate to do all kinds of mixing of the information, otherwise would be entirely element-wise. And there's also some extras. So for example, we allow computing length. We'll see how in a moment. We allow composing selectors. Again, we just assume that Q and V will somehow figure it out later in the true transformer. So this is just about our convenience. And we allow functions. This is just so that we don't have to, so this is entirely kind of sugar, so we don't have to repeat code a lot. So in range describes checking that sequence operator val is greater or equal to some either value or other sequence operator min, and smaller or equal to some either value or sequence operator max. So we can check which of our indices, for example, is between 1 and 3. And on hello, we see it's true only at, 1, 2, and 3. And we have library functions. So it's actually possible in all that we've seen so far to implement functions like selector width. So to actually take a selector, even though we've only been thinking about aggregating it so far, to really take a selector that we've created and check how many other positions each output position, each query has focused on in this selector. So for example, if we create a selector that focuses each token on tokens equal to itself and apply selector width to it, we effectively get an in-place histogram on the tokens that are in the sequence. And we can also do a count. So we can check, for example, how many L's appear in our input sequence. And for a small example, let's compute length. So what we're going to do for length, first of all, we're going to focus, we're going to create a selector that focuses each output position on every input position. Here, technically, we could apply selector width because we have that function, but we do actually want to understand what's happening here. So let's take a closer look, especially that I haven't proven how selector width exists yet. So we're going to use something called indicator, which just converts Booleans to integers. So true becomes 1, false becomes 0. And we're going to put a 1 exactly where the indices are 0 and otherwise 0. And when we aggregate on this indicator with our full selection pattern, then we'll choose 5 positions, because that's the length of our sequence, all positions, but only grab a single 1, because only the first position contributed a 1. And so we'll actually get the inverse of our length. We have to divide this 1 by all of the positions. And then just by computing the inverse of this result, then we get the actual length of our sequence. Does that make sense to everyone? Okay, great.
I have a comment.
Okay.
So I feel like, this does make sense. And I think it's cool, but also I feel like layer norm could complicate this type of computation if you added layer norm after the attention head, because it would kind of normalize away the 1/n factor, right?
Yeah, that makes sense. So yeah, it's entirely possible that layer norm would hurt this implementation. We could think of a different way to implement length. So this way uses only a single attention head in a single layer. But maybe we could do instead have each position try to focus on its next position. And then the position that doesn't manage to do that would know it's the last position. And in the next layer, it would tell everyone in its key that it's the last position and contribute its position for everyone else to know the length. That's another solution we could implement.
That makes sense. Cool.
So I don't know which, but we hope. Definitely.
So I had a question. So just if I understand it correctly, so the first part, the 1/n thing, so that's done by attention, and the feedforward network will
hang on. Which part?
So forgetting about RASP for now, just I'm trying to think how the transformer will implement this. So the 1/n thing, so if 1/length, so that is implemented by the attention, and then the inverse is done by a feedforward network, right? Or are there more components involved?
That's, the layer contains more components, and indeed, as Will suggested, it's possible that the layer norm would hurt that. Yeah. So but this solution uses only the head and the feed forward.
Yeah. So is the feedforward network? So is the inverse, the network to compute inverse, is that very large? So how
That's
how
a
many
good that's a
parameters
good
is
point.
it
So
very
I don't
large?
know.
Is it
I
very
don't know. It's possible.
hard to learn?
It's possible.
Uh,
Okay, so you're asking good questions, and I'm glad that there will be an example in a few slides where we see, if you remember a few slides ago, we showed computing reverse in RASP. So while there's a lot of question of how would we compute inverse, that seems hard. We're going to see in a couple slides that nevertheless transformers do manage to learn reverse, and they do manage to learn the flip selector. And admittedly, that was for relatively short sequences of lengths, I think 50 to 100. But provided, we always deal with the bounded length sequences, so it somehow managed to learn this map. It's possible that for particularly long sequences, the network would be very large. Okay, so we continue. So let's really take a look at how would we analyze a RAS program once we've got it. So the indices and tokens, they're the input. They don't require any layers in a transformer. The select and aggregate pairs are effectively just attention heads. We can only apply such a calculation once all the inputs, once all the variables to that calculation are ready. So whenever we make a selector pattern, it has to be in a layer that's after all of the values that it uses. So it opens a new layer after its dependencies. And similarly, its aggregate must be after all of the values that it aggregates are ready. So select aggregate pairs generally open a new layer relative to their dependencies. But we could have multiple such select aggregate pairs in a single layer because we know that there's multi-head attention. So if there's no dependencies between them, we can stick them in the same layer. And feed-forward operations, we say, okay, that happens at the beginning of the layer, so we don't add layers to them. Maybe we should think if there's feed-forward layers and no attention heads, then we should have at least one layer to allow the feed-forward operation, and that's it. Or they're at the end of a layer. Anyway, okay. And so let's look at how this translates to a simple RASP program. So we've got the reversing program. We do the flip and the reverse. So the first things, the most basic things, are the indices and the tokens. They come at layer 0. Then length, we saw a moment ago, we actually create with an attention head. At least we think with a single attention head we will succeed. So that creates a new layer. Then length minus indices minus 1 is computed in the feed-forward layer that comes after that head, in the feed-forward sub-layer that comes after that head, so in the same overall layer. And then that is all used to create a new selection pattern flip in the next layer, which then aggregates the flip and tokens already at this point to create reverse. So if we draw that, that might be a bit nicer. We begin with the full attention pattern that created length. So it just focuses every output position on every input position, broadcasting a 1 from position 0 and 0 everywhere else, getting 1 over the length of the sequence. Then we compute the, when that's aggregated, we get that 1 over the length of the sequence. So that's our first head. Then we compute the inverse of that to get the length itself. And then inside the same feed-forward layer, we also compute length minus indices minus 1 to get reversed indices. Then we create another head that matches the indices with the reversed indices to create our flip selector. And then we aggregate the tokens with that flip selector to create our reversed sequence. So that happened in 2 layers. And now, is that connected to reality at all? Can an actual transformer do reverse in 2 layers? Will an actual transformer make the same kind of selection pattern? Let's find out. So we train an actual transformer on reverse. And from RASP, we have this prediction that we need 2 layers. And let's check A, if we've written an optimal program in RASP. Could we have done it in 1 layer? And B, if our prediction that 2 layers is enough, is indeed true. Can the transformer do it in 2 layers? And we do find two things. First, on 2 layers, we managed to reach 99.6% accuracy, reversing input sequences of lengths 0 to 100 after 20 epochs. So 2 layers is enough. And second, it seems that we've made an optimal program, because if we reduce to only 1 layer, even if we compensate and use 2 heads or twice as many parameters or whatever else, we just can't get very high accuracy, even after 50 epochs, because it doesn't know to deal this changing sequence length. And as a bonus, we even get the same attention patterns. So the first layer seems to have used a uniform attention, presumably to somehow compute the sequence length. And the second layer has created very nicely the same reversing attention pattern, focusing each output position on the opposite input position. At this point, I think we're at 50 minutes of me talking, so I won't go into this next example too much. But for histogram, just an in-place histogram, then we have some kind of RASP code that does it in a single, maybe, I don't know, it depends on how you're feeling. Would you like to go through the example of in-place histogram? Okay, let's go through it. So what's in-place histogram? So it's something that we mentioned a bit earlier in the talk. At each token, and we are assuming a beginning of sequence token here that we ignore. So at each token, excluding the beginning of sequence token, we're going to output how many times that token appears in the input sequence. So for example, on ABA, we output 212, except for a 0 on the beginning of sequence token. For hello, we output 11221 with 2s on the Ls. Now, one way to do histogram, because we have this selector width function, is just to do the selector width of the selector that focuses each token on the same token as itself. But in this example, we do want to really understand how that would happen. So let's actually do a selector width when we're allowed to assume that there's a beginning of sequence token, because that's slightly simpler. So the first thing we're going to do is we're going to focus each token on the same token as itself. So that's select tokens equals. And we're seeing an example of that selection pattern on hello. But then we're also going to focus on the first position, on the beginning of sequence token. So we're also going to select wherever the indices are 0, and we're going to apply a logical OR between them. And so we're going to get this attention pattern, which focuses each token either on itself or on the beginning of sequence token, both of them. And then we're going to again do this aggregation like we did for length, which broadcasts a 1 from the first position and a 0 from everywhere else. And so we're again going to get this behavior where we divide 1 by the number of positions that we've focused on. And now, if we invert this and remove the additional 1 that we got from the beginning of sequence token, then we get the in-place histogram. Does that make sense? Great. So if we look at that in RASP, we only used a single attention head, which was a combination of 2 attention heads, but ultimately we applied aggregate to a single selector pattern. And that head is just focusing on all positions with the same token and on position 0. And when we train a transformer on this task, then we get the same pattern. So here's an example on some input sequence. And on one side, we're seeing how RASP deals with that sequence, what selector pattern it creates. And on the other side, we're seeing the heat map for the attention head in our trained transformer on the same pattern. And we're saying that it's the same thing. So it's learned the same solution. And that's really cool. Now, in answer to previous questions, it may be that it's only managing to do this because these are relatively short sequences. So it's easier to compute the inverse, and it's easier to compute the Q and K and so on. So it may be that this gets difficult with long sequences. But at least for short sequences, we're seeing this match, and that's, I think, really cool. And I think that kind of concludes the introduction of RASP. So we had the sequences, the element-wise applications, the selectors and aggregate, all the shortcuts of functions and sort of library functions like length and like count and selector width. And then there's a little bit of insight that comes from this. So for example, there was the universal transformer, which talked about repeating a transformer layer multiple times. If you think about it, any sequence operator you create in RASP, even if RASP itself has function definitions and possibly functions calling each other, and maybe RASP itself is very strong, every sequence operator is the result of a finite number of operations. So it's not an infinitely powerful language. It's a finite number of O(n) squared calculations. It's not a Turing, the sequence operators themselves are not Turing complete. And if we want to be able to do an arbitrary amount of calculations of operations on our input, then we need this ability to have true loops, like the universal transformer tries to introduce. And we have the sandwich transformer, where Press and colleagues sort of said, hang on, in a transformer encoder, it's always self-attention and then feed forward, and then self-attention and then feed forward, and always in these pairs. But maybe they don't have to be in these pairs. Maybe reordering and having first a lot of attention heads and then a lot of feed forwards, or somehow some other arrangement would be more effective. And I think they did find that it's better to have a lot of attention heads and then a lot of feed forwards. I think not pure just attention heads and then just feed forwards, but it is, they did see that they don't have to be joined together. And that also makes sense in RASP. There's not much point to doing the element-wise operations before doing a bit of aggregation to get all the information that we need. For example, we can't really do reverse until we've aggregated and computed the length. So I don't know, I think that's nice. Another way of seeing that there are two different things. And there's also, this is something, the attention head effectively creates n squared scores because it creates a score for each two positions. And so the computational cost of an attention head and so of a transformer encoder entirely is O of n squared. So maybe we're asking ourselves, is it worth it? Like a recurrent neural network, it runs in linear time, I think. Yeah. Is this n squared computational cost even giving us any kind of additional power? So we may not know that there's a function, like just because we haven't searched for it. We may not have found in this work a result saying, yes, there's a function that requires n squared computations, and indeed it can be computed in RASP, so the transformer cost is worth it. But at least we can implement arbitrary sorting in RASP, which at least suggests that n log n of the massive cost can be exploited. So that's something. It's a bit more wishy-washy, but it's nice. And that's it. And we did implement RASP. There's a REPL. You can really download it and install it and write RASP code. So I really encourage you to do that. And that's it. That's RASP. And if you have questions, I'll be happy to answer them. And if you don't, I can make them up. So whichever. Yeah.
I have a question. Can I go?
Mm-hmm.
Okay. I'm not sure I understood everything, but maybe I need to think a little bit more. But let me ask. Okay. Mm-hmm. So think that you have only one head. Okay. Mm-hmm. Because I don't understand the multi-head yet. So if you limit the architecture to only one head, what you have done is you have been modeling the attention machinery using this select predicate, where you take, there is, one token making the query, and mm-hmm. all the other token are, have a key, and they respond to that, Mm-hmm. So basically, this you have modeled this using a binary relation. Like the third argument in select is a binary relation. Now, my question is this. If you move to a model where you have relation of order 3, like you don't have only binary relation, but you have relation in which you can compare one token to 2 more tokens, okay, and sort of higher order attention with a single head, will you get more power or not?
I haven't applied the thought to that, but I imagine you would. I guess if you could prove that with such a model you can compute a function that takes at least greater than ON squared operations, then you would know that you've definitely increased the power. I would imagine, for example, if we were talking, this is very hands in the air, I haven't thought about this. We were talking about how we would compute length a moment ago. So imagine the second solution, which is every position tries to look at the next position, and then only if it doesn't have a next position, then it knows it's the last token, and so it's the length of the sequence. Then maybe if you were using triplets, you could already in a single layer figure out what the last position is. Wild guess. Don't want to promise. And I don't know if that would necessarily increase the power, because anyway, you could do that in 2 layers with a normal one. But I imagine you could somehow increase with triplets.
Okay, interesting. So when you do the select, you don't have any longer a 2-dimensional matrix, you have a 3-dimensional matrix, right?
If you were doing that, yes.
The third order, okay. So it could be that transformer, raised to the third order will be more powerful than transformer of second order.
I would imagine. You would have to think what you would do with these. So what would you be aggregating exactly there would have to be a lot of
okay.
Yeah, and of course it would be more expensive.
Okay, no, of course. I understand. Thank you very much.
No problem.
Thank you very much.
That's an interesting question. Anyone else?
Yeah, so I had a question.
Mm-hmm.
So I'm not sure if I might have missed something, but I wanted to just know your opinion on how much do you think residual connections play a role in your RASP computations? Like if you want to try and implement something, then how important are residual connections there? Because I mean, for the encoder decoder network, so we know that so if you remove a particular kind of residual connection, so they are not Turing complete. So there they kind of play a big role in a particular residual connection. And for the encoder only case, the last few weeks back, the paper that I was talking about, so in those experiments when we removed the residual connection, so then the performance used to decrease drastically, empirically. But I'm not sure theoretically how does it affect the expressiveness of encoder only networks. But I assume it would somehow. But what is your
So I think the residual connection is very important to RASP. It doesn't appear as an operator because it's not like an operation in the sense that it's changing anything to me, but it's the retention of information. So the fact that even after I've computed indices +1, I still have indices. Or even after I've computed reverse, I still have the original input in the correct order. So to me, the residual is the fact that a variable that I had, for example, at line 3 in my RASP code, I can still use at line 10, even though I've created new variables between the 2 lines.
So you keep residual attention. So layer norm is the only thing that is not involved within RASP. Yeah. Okay.
So it looks like you have residual connections from all previous layers simultaneously.
You could see it in that. I see the fact that the residual connection happens in every layer as the sort of continuation of okay, I had all this information, I still have it. and that then at the next layer, we had all this, we still have it, and so on. But yeah, we're always keeping the information.
Yeah, so in practice, to some extent, transformers are bound to lose information with each layer, right? Because you cannot really add to information, you can only lose it and maybe restructure it in some way. So I think at some point, when the depth of transformers becomes really, really huge, they may deviate from the RASP model considerably because of how much they have to forget, basically.
You're reminding me of a paper which unfortunately I don't remember the name of. I think in ICML or something, decrease in exponentially. I'll send it afterwards when I find it. But there is something that if you remove from a transformer, it really loses its information very quickly, I think. And yeah, it makes sense that with the depth, it would sort of the information would become very fuzzy. But we could also hope that if it recognizes that particular information is important, then it will keep it for as long as it needs it. At a very extreme case, you could imagine a very long embedding, as long as we need for the depth of our transformer, where every time new information is created, let's say in positions 10 to 20, and then the initial embeddings were only really in position 0 to 10, and everything else was 0. And then the residual connection adds back what was there before. And then you go to the next layer and create new values in 20 to 30. And then the residual connection adds back everything you had before, and so on. So obviously, it doesn't look like that, I think, in any natural transformer, but technically, it could overcome this. So I think that's the end of the questions. I can stop the recording and we can chat normally if there's any.